What happened? What's this noise? ये class के अंदर है बाहर? Huh? But this suddenly just escalated. Yeah. Okay. Let's go. So you have a population and it has some n elements, and there is some attribute associated with each member. Now this attribute would be something quantifiable. So it could be like height, salary, age, something like that, which you can give some number or some binary value, yes or no answer, or some categorical answer if you are in category 1, 2, 3, or 4. So in a sense, this thing can always be quantified. So it's a variable. And in what sense it's a variable? Because it takes different values for different elements of the population. So for example, I can line up all the population elements and I can just record what is the value of this variable. What happened again? Is there someone who can help us with this? I think it's better to not come to this class if this is going to happen all the time. It's extremely distracting. Is it coming from outside or from inside? So now we're going to pick, now what I can do, I can talk about the distribution. Of the population. For this variable x. So for example, they could be like, so what is this distribution is telling me? It's telling me that if I plot this variable, if I draw a histogram, then how many times a particular value of x is found in the population. So it's just tells me about the frequency of different values. Now, for example, I can just take this is just example from the book. This is the first example over there. So there are 6 employees in a company, and they have a certain number of years as experience. And there are 2. The first one has 2 years, the other has 4, third one has 6, fourth has 6, 7, and then 8. So what you have over here, I can just list that this variable x is now the number of years of experience, and I can plot. since it's a discrete variable, so would be fine if I do a dot plot or a histogram. So 2 has 1, there's nothing for 3, there's 1 for 4, nothing for 5, 6 has 2. So this bar plot, this is the distribution. And over here, I have the number of elements in population which have this much frequency. Now, I can also do one more thing. I can give it the form of something which looks more like a probability. Although it's not a probability, it's just the frequency. I can make it a probability plot by dividing by, if I divide frequencies, over here is the frequency in this plot. If I divide frequencies by total n, then I'll get something like I have 6 elements over here. So it would be 1 by 6. This number is 2 by 6. And this will look more like a frequency plot. Because when I will, so this I can call something like P of xi, where xi is a particular value. Xi is a value of the variable x. X. And P is just, you have taken the frequencies and divided by the total numbers, is n of xi, where n is the how many times you have it in population, and divided by the total number of members in the population. The thing is like that if I add, let me write it this way, Pi is Ni, where Ni is the number of time you have xi. The thing is that if I add all of these, since when I add all the numbers which are present, this is going to sum to n, so I get 1. So this thing has properties of a probability. It looks like a probability, but it's just the frequency. Now, if I pick some samples from this distribution, so I have this population and I pick a sample of size 1. Then which one of this will come up? Well, each member, this is the main assumption of independent sampling, is that each member of the population is equally likely to turn up in my sample, but not each value of the variable. So each member is equally likely, but the value of the variable is not equally distributed among the population, because some values have more members in the population having that value. Like over here, the value 6 has 2 members. So if I independently pick, I have twice the chance that I'll pick some guy with experience of 6 years compared to the guy with experience of 4 years. So if I randomly pick, first of all, when I pick a sample of size 1, this would be a random variable. X will become a random variable. So it will take random values. And now I can assign probabilities to the values of x. These will be just the probabilities which I defined above. Because that's how you actually define the probability. That's the very definition of probability. That you just count the frequencies. So if you are independently sampling and you're sampling a great many number of times, then you expect that each one of the members is equally likely to come up. So those members which are more over there, they will turn up more of the time. And how will you count the probability? You just count how many more numerous they are. So this would be just the thing which I defined. The number of times this value is prevalent in the population divided by the total population. So when I pick a sample of size 1, that becomes a random variable, a truly random variable, and the probabilities are just those which are the frequency distributions in the population. So this random variable of size 1 has same distribution. Random sample of size 1. I apologize for bad writing today. This will not be the case next time. And I'm just trying to find the optimum way to do this lecture. So hopefully next time I'll have something much better. First of all, I'll have my tablet back, but I'll try to speed it up as well by writing a few things beforehand like I did last time. So random sample of size 1 has a probability distribution which is identical to frequencies in population. Well, actually, this is exactly the definition of probability. I think this is exactly how you define probability in last semester. You have a great number of things and you are picking from there. This picking, you can assign a probability and you assign it to frequencies. So sampling through one member, just one member, is just exactly the definition of probability. And we can do something similar for infinite population. So like, for example, you have, in this case, you cannot exactly give the frequency interpretation. You give frequency interpretation by assuming that you have tested this thing for a very, very large number of samples. And you have some population over here, living over here, for which you have assigned some probability. Either they exist, which you do not have access to, or you are told. So you have a variable whose values are plotted here. And with each value, you are given a bar plot, that what is the probability. So like, for example, my infinite sample could be, infinite population could be the coins. You're constantly flipping the coins, or you are constantly monitoring the heights of babies who are born. Is not going to stop. Or if you have coins, you don't really have a population of coins, but you have a belief that you have these two values, head and tail, and call 0 and 1, maybe. And you are giving them equal probability of half. So this is the distribution in the population. Now, if you will pick a random sample, this is exactly the distribution which will be in the sample of one element. But what if you pick 2 members? Now suppose we pick.
Excuse me, sir.
G.
Sir, ये infinite population कैसे है a coin toss? Because we have distinct possibilities. It can either be head, it can either be tail.
Yeah, okay, so that's a very good question. This is a confusion which must be cleared. Like, for example, मेरे पास population, let's make this confusion cleared by first considering a finite population. So suppose आपके पास 100 pens हैं, and they come in 2 colors, red or blue. Now your population size is 100, but your variable is the color of the pen. And that has only 2 possibilities, red and blue. So, and suppose you have 60 red in the population and 40 blue. So when you will draw the distribution, blue, red, then it looks something like this. 40, 60, or if you give them the form of a normalized frequency divided by the total number. So this would be 1 by 4, and this would be 1 by, this would be 4 by 5, 4 by 10, which is 2 by 5, and this would be 3 by 5. Because we're dividing 40 by 100 and 60 by 100. So your variable, that is different from the number of elements in the population. So like sometimes you have like each element in the population has distinct height. So for example, if I'm picking 10 students and all of them have different heights. Now each height variable value is equally likely because all of the students can be independently picked with same probability. And so in this case, the values which the variable can take matches with the number in the population, but it doesn't have to be the case like in this example. So similarly, like coin toss. How many times, if I have just in my mind that there's this abstract probability which exists, so it exists if you check the coin by tossing it like infinite number of times. You're not actually tossing the coin, you just have it in your mind that there's a probability associated with this event. And how many times you can toss in principle? It's an infinite number of times. You can have infinite number of coins and you're tossing them, or you're tossing them infinite number of times, but the possibilities which you are checking are only 2.
Sir, I have a question.
Yeah.
Sir, तो हम जितनी बार coin flip करेंगे तो वो हमारी population हो जाएगी?
नहीं, वो population नहीं हो जाएगी. It's just an example of infinite population that coins have been checked an infinite number of times. Not so when you're talking about an infinite population, it's a tricky idea because there's nothing truly infinite in the world. You just have in your mind that there's some probability which exists. Probably this is not a very good example if I call them infinite. We could talk about if you want to talk about something truly infinite, we have to really go into abstract things. For example, I don't know if numbers of stars in the world are infinite, or something which is not stopping. So, and you're not proposing them to stop, like how much would be the population of the world, something like that. But the idea is that you do not always have to actually count the frequency of the things in the population to assign them a distribution. You can do that, So like in the first example, or in this example of pens, you have 100, and you can count how many are red and how many are blue. But sometimes you do not have this kind of luxury that you can count all the population. And sometimes you do not give probabilities this way when you have in principle infinite number of elements are there. So like for the coin toss, it would be saying that you can do it infinite number of times. And each time gives you one member in the population. But that's not the best way to describe. The way you do it, you check it a large number of times. So in a sense, from an infinite population, you take a very large sample and check the probability distribution over there. Check the frequencies over there, and you make a distribution based on that. So once you have that distribution, this you would consider the distribution of population. And now your belief is that anytime I pick one sample, one single sample, it will have the exactly same probability distribution as which I have assigned to the population. So actually this idea that you pick a sample of size 1 from a population, I suppose this is something which you have done in the previous course, because that's how you define probability. That you have a large number of trials available. So what would be the probability that if you pick one? So sample of size 1 is not different from what you have been doing in the last course. So over here, just for concreteness, I'm saying that you have a population, and if infinite populations confuse you, you can keep them aside for now and just focus that you have a very big sample. Well, not necessarily very big. You have some sample, you have some population, and it has some frequencies associated with it with different values of the variable. And when you pick one, its probability is exactly what I was calling the frequencies over here. I gave the example of coin toss to tell you that sometimes when you sample, you do not think, you are not thinking in terms of frequencies. Someone has done an experiment on this coin, they have tossed them a huge number of times, and they have told you that we believe it's a fair coin, and the probability distribution for this coin is half and half. So now it becomes your belief that when I'll sample picking one, the probability of head or tail would be half. So in a sense, in a way, I shouldn't even differentiate between the probability distribution of the population and the probability distribution of sampling. It's just like, to be very precise, we make a distinction, because when you have a finite population, then there's not really much point in talking about probability. Probability occurs when you take the limit of samples that you have sampled a very huge number of times, an infinite number of times. So that's the only reason. When you have a population, finite population, you can only talk about frequencies. And when you have a population, I don't know, I mean, there's no random variable there. There's a variable, like in this case, the number of experience. It varies from member to member, but that's not random. It becomes random when you start sampling. So you define your random variable to be the number of years of the person which I pick at random. This variable is a random variable because it's going to have, you cannot predict what value it will have. It will have some random value, but not completely random. There's a probability distribution associated with it. You cannot predict at any given pick that what would be the answer, but you can still assign probabilities. So any more questions? So now suppose if we pick samples of size 2. So I'm continuing with my example, which I had. So the numbers were 2, 4, 6, 6, 7, 8. Now, first of all, what are now my variables? Now I have a pair of variables. I pick one, and then I pick another one. I have two random variables because I make a sample of two things. They're same variables because in both cases they're similar variable, I should say that, because in both cases I am looking for the number of experience of the person who I have picked. And the probability distribution is also same because I'm picking from the same population. So it's like the same random variable, you have just made another copy of it. You have a pair of random variables, but they both are exactly same. Well, you have to be a little bit careful when you say exactly same. They are in some sense not exactly same, and let me say in what sense. That comes because of this distinction, which is sampling with replacement and sampling without replacement. So what is sampling with replacement and without replacement? So so again, I had this list of 2, 4, 6, 6, 7, and 8. And if I say I'm going to pick two numbers from this list, and the first number is 2. So then the first variable was a random variable, and the probability of getting a 2 was 1/6. But now if I say that I'm not going to place it back in my list, I have exhausted this 2, and this member of the population which I have picked up is not going to go back. I'm not going to choose it, try to look for it again. I have chosen it and it's frozen. Then I do not have the same probability distribution for the next variable, because now I cannot pick 2. 2 now has 0 probability. So I can only pick 4 or 6, any one of those. So the probability distribution of the second variable gets affected a little bit depending on what I have picked the first. This happens when you are doing without replacement. Causes the two variables to have different probability distributions. But if I allow that, I'll pick and I'll put it back and then again randomly choose. Then obviously if I have a 2 here, I still have 1/6 probability that I'll again get a 2 here. So in that case, the two variables become exactly same. Exactly same in the sense that they both have exactly same probability distribution. So both of these things are valid. Sometimes you do it with replacement, sometimes without replacement. Practically speaking, when you have a large population and you are selecting people from there, like for example for a survey, then you are not replacing, because you have chosen one guy, you do not go to him again, you choose someone else. So many a times you are doing without replacement, practically speaking. Huh? Causes the two variables to have slightly different probability distribution. However, if you have a very large sample, if you have a very large population and sample size is small compared to the population, then it doesn't really matter that if you are doing with replacement or without replacement, because picking one element does not change the probability for the rest. So for most practical purposes, I should say for large samples, large population compared to sample size, without replacement, is just like with replacement. So like you have 1 million people over there, you pick one, it's not really going to affect the probability for 999,999 others. So for large populations, you can just assume that they are same kind of variable with same probability distribution. For small populations, there is you have to be a little bit careful. I'll just mention how the formulas change. For most part, we will assume that as if they are exactly the same variables, and where the formulas change, I'll indicate for the small population size. G. Yeah, exactly. So now, if I have going back to that, when I choose 2, I have 2 variables. Now, first of all, what is my space, sample space? What values they can have? Well, they can have, I'm doing without replacement, which is the most common thing. So you have 2, 4, 2, 6, and I'm just counting what would be the frequencies. So I can have 2, 4, 2, 6, and then I can have the pair of this guy with the other guy who also has 6 years of experience. There are 2 people in the population which have 6 years of experience. So when I can pick this first guy and this guy with 4 years experience, and this first guy and the other guy with 6 years of experience, and again this guy with 2 years, and the other guy who has 6 years of experience. Similarly, I can pick this, and I can pick these. I could have probably given them some names and then just written out what are the possibilities of the elements. Then I have 4. I'm just counting the sample. So the order doesn't matter. I'm just counting which members of the population can be there. So order doesn't matter. So I don't go backwards. I won't have 4, 2. But I'll have 2, 4, 6 because 2 members have the value of 6. 4, 7 and 4, 8. I just want to do everything by hand today so that it's clear, and very soon we will be moving to R. Now I have exhausted the list where I have 4s. When I keep it as, like I had kept 2 as the first, now I'm not going to put 2 in the second column because the order doesn't matter. Now I have 6, 6, 6, 7, and 6, 8. But now I have the other guy. This guy who was here, he comes over here and I can make this pair again. So maybe I should write A and B. This guy A, this guy B. A, B. A, B, order doesn't matter. So I will not have 2 such pairs. A, B, B. And then I have this. Why did you do this, Anas?
Oh, sir, I'm sorry. I thought it would just appear on my screen. I was trying to take some notes.
So you have this distribution, and now you can count the frequencies, for example. So you can say that the value of 6, 6 appears once. How many you have over here? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 in total. So having 6 and 6 has 1/15 probability to appear. But 4 by 6, 4 and 6 has 2/15 probability appearing. So with this sample, you want to do, wait, let me try to erase this. Can you remove it on us somehow? Because it's traveling with it. I don't know what to do with it.
Yes, I did.
Okay, thank you. Now, what can I do with it? So you want to, so what we have seen is that when I pick one variable, I get exactly the same distribution as the population. And if I want to have some idea about something about the population, I have to do as much work on one variable as I doing on the population. So for example, you want to know what is the mean of the population. Now to compute the mean, so what is the mean? Mean of population. This is some characteristic about the population which you want to know. This is some information you want to know about the population. Let me give it a symbol mu. I think that's what they're writing in our textbook. This is just an arithmetic concept. It's just the sum over all values which the variable can take times their frequencies. Because you're just adding all the members. You take all the members, add all their values, and divide by the total number of members. But this is also then this thing. But it's just an arithmetic operation, adding all the things and dividing by the total population. So like for in our case, it would be 2 plus 4 plus 6 plus 6 plus 7 plus 8 divided by 6, it comes out to be 5.5. Now suppose you want to compute this mean, or you want to have some idea about the mean, and you take one sample, what are the chances that you will hit the mean? Very little, because you will either land on 2, on 4, on 6, or 7, or 8. You will land, you have some distribution graph. These are the values. There's somewhere you have a mean, and you have some distribution graph. You don't know. And all these things are very, very likely to appear. So when you sample, you may get this, you may get this, you may get this, you may get this. However, you can do this thing. This is just a mathematical concept. If you do this thing, this is called, just to give it a different name from the arithmetic operation of mean, of adding a bunch of numbers and dividing by the total number of numbers. You call expected value or expectation value. Different people have very similar sounding names for it. I'm used to of expectation value. Some people call it expected value, or some people just call it mean, average. This is a probabilistic average. Expectation value of a sample of size 1. What is this? Each value you can get times the probability that you will get it, and then you sum over it. But since these probabilities were equal to the frequencies in the population, so this is exactly this mean, which is the expectation value of a sample of size 1, a random variable you picked up. This expectation value or this average value is equal to the population mean, or average value. So I'm going to stick to this. When I say average, I mean probabilistic average. Average value of a single randomly sampled variable is equal to the population mean. Now, you will not, to get the average value, so what is telling you that the expectation value of the sample will be equal to population mean. So if you want to get the population mean, you can find out the expectation value of a sample of size 1. But to do that, you will have to make many number of trials, because it has, when you will randomly sample, you will not land on the mean. You will be landing at different points, and you will have no idea what the mean is. You will have to make a large number of samples and then compute their expectation value, their mean. So you cannot get the idea by a few number of samples. You need a large number of samples, and how many you need, and it depends on what kind of probability distribution you have, how broad it is. If the probability distribution were like this, all centered here, then you would be, then what would happen is, like, even if you randomly sample, you are pretty much assured that even the one value of the sample will be very close to the population mean, but not in general. Now what I do is, I will use these things later. Let me go down here. I compute the mean, let's call it the mean of sample. That's not probability mean. That's the arithmetic mean. What is the mean value of the two numbers you have got? So all you do is sum these. So I now I have got the mean of sample is, what is this? Is the sum of values in sample divided by number in sample size, I should say.
So sir, mean will be different for every sample. For example, if I
Yeah,
have-
exactly. Mean of the population is fixed. It's just one number. But when I pick a sample of 2, for example, every time I'm getting a different mean because I get different numbers. So mean of sample itself becomes a random variable. So like over here, it's 3. Over here, it's 4. Over here, it's 4. It's 4.5. It's 5. And here it's 5, 5, 6, 6, 6.5, 7, 6.5. Is it 6.5? Yeah. This is again 7, and this is 7.5. So first of all, when I'll pick a random sample of 2 numbers, the mean will hop. Mean of sample is a random variable. I'll get a different answer every time for the mean. If it's a random variable, I can talk about its own probability distribution. And how would I get its probability distribution? You have a question? You have a question? And how would you find its probability distribution? Well, the same idea you have for how you find the probability distribution. You repeat this experiment a huge number of times. And from this sample space, you can just count, since each one of them is equally likely, because I have counted all the possible samples I can get in terms of members, not in terms of values. So each member is equally likely to turn up over here. Each this bracket is equally likely to turn up over here. So each one of them is equally likely. But not each value of mean is equally likely. Like I can see that 5 turns up 3 times. So its probability is 3 by 15. While 3 turns up only once. So its probability is 1 by 15. So I can draw I had tabulated them over here as well. These are the samples and these are the sample means. And I can compute this probability by just counting that how many times a value turns up over there. So in any case, since sample mean is a random variable, sample mean, which I will denote by x bar, is a random variable, so it will have a probability distribution. Since we are for now mostly talking about discrete variables, so probably a much cleaner way is to draw bar graphs, because I have only discrete values. So sample mean becomes a random variable. But what if you, and here again I have just
Second, can
drawn.
you scroll up?
Yeah.
Just a second. थोड़ा सा और. Thank you. I've got.
No, I
Thank you,
have
sir. You can
got.
continue now.
No, I have got this sample mean, and I have got the probability of for each one of them. Now, what I can do, I can compute the expectation value. Sorry. I can compute the expectation value of sample mean. Some people just call it, to be cheeky, mean of the sample mean. Some people call average of the sample mean. So it's just that mean, sample mean is a random variable, and now you're computing its probabilistic average value, its probabilistic expectation value, which is just, since sample mean is a random variable, you compute the probabilities and you do this. This gives you the expectation value of the sample mean. Now, just for fun, so just for fun, if you compute the sample mean for this thing, for this data, you are given all possible values of the means and you're given the probabilities. So if you use this thing and compute the sample mean, if anyone has a calculator, can you do it? And remember, the population mean is 5.5. Let me quickly do it over here. I had this calculator. Huh? You have to use this formula. So all you're doing is this. From this data, 3 into 1 by 15 plus 4 into 2 by 15 plus 4.5 into 1 by 15 plus 5 into 3 by 15 and so on.
Sir, can we add all the sample means and divide by 9?
No, you cannot do that. That's not the formula. It's a probabilistic mean. It's not the arithmetic mean of all those values. All those values are not equally likely. So it's like you're computing the mean by taking these samples by huge number of times. And then you do the arithmetic mean of all those huge values, that would be the expectation value of sample mean. So sample mean hops.
If the probability was the same, then can we do that?
Then you can do it. Yeah, obviously. If the probabilities are same, then you can do it. But in this case, they are not.
Sir, could you explain again what exactly is like the purpose of taking out the expectation value again? Like in words, like in practicality, like what, how would this be helpful exactly?
We're gonna move towards this. That how it's gonna. So we are just building it up. That why it will be. It's an interesting thing to look at the expectation value of sample mean, because if you just finish this calculation which I told you, you will find something kind of strange. Yeah, it's 5.5.
Sir,
Wait. So there's this interesting fact that when I took one variable and computed its expectation value, that was equal to the sample, the population mean. And now what I did, I took samples of 2, computed their mean, and took the expectation value of that mean. And that is also equal to the population mean. And actually you can check, take it as an exercise, take samples of size 3, size 4, size 5, any size. Once you take a sample of any size, compute its mean, sample mean, and take its expectation value, it tells you that it's equal to the population mean. Now, practically speaking, so this question was, practically speaking, what does it tell me? Why would I need it, and what is it telling me? Well, the thing is, like, whenever you have a random variable, it's something which you cannot predict. So in a particular experiment, like when I pick one random sample and I compute its sample mean is just an arithmetic operation on it. I don't know what value will turn out in that case. But there will be a distribution. And so you want to have some idea of distribution, that these different values of sample means, I wanted to do something with this sample and to get some idea about the original distribution. But every time I get a different mean. And can I do something with this mean? Since you get a different value every time, you still want to make some statement. Since it's a random variable, what you want to know is that how this hopping is happening, how it gives different values at different times. Given that I get a different value every time, what can I say? What can I conclude about the data of which I'm trying to make a statement about? Well, if you are making a statement about random variable, you are basically want to know its distribution, like this thing. This will have all the information about, if you randomly check, what will happen. But a very interesting quantity, one of the most important thing which you can say about the distribution is its expectation value, its mean value, which is equal to that if I repeated this experiment a huge number of times, if I took these samples 1 trillion times and then I computed the mean of the mean over that data, what would be the answer? So it somehow, in a sense, tells you, in a way, some central value in this distribution. And you know that what is the other interesting thing? One thing is you want to know that what is the value around which it is distributed. It may not even be the most probable value, like in this case, this distribution looks like the most probable, but it could be even least probable. Like if you have a distribution like this, your mean is here, but this value is least probable. But at least it tells you like what is the point around which you will have values distributed around. So it somehow gives you a central estimate of what is the value around which your random variable is spread out. And the other thing which is extremely important to get an idea about this random variable is its standard deviation, or its square, which is called the variance, which essentially tells you how broad this distribution is, which tells you, okay, this is the central value, but what is the chance that I'll get something very far away from it? So standard deviation is like where you will have some appreciable chance of having some values in that range. You go beyond that, your chances are decreasing. So these two things are essentially one measure of telling you about what kind of random variable you are dealing with, what are its main characteristic. So you are making a statement about its probability distribution, and the first few things you can check is its expectation value, and the second thing is its standard deviation or variance. Yes. Yeah, if it's not random. So yeah, this could be, for example, a check. You take samples. So for example, your problem is not such that you want to infer something about the population. So suppose you know about population, and you're just doing some samples and doing something to them, and you just want to make sure that you always pick random samples. So what you can do, and you're not bound by some kind of limitations. So what you can do, you can say, okay, I'm going to take 1,000 samples, compute the mean, and check if it's equal to the population mean. If it is, that means this is an indication that you are probably picking up random samples. But if this fails, you immediately know that you're not picking random samples. Yeah, so it was a very good question. Both questions were very good. Now, so my claim is, it looks like from this calculation that the expectation value of sample mean is equal to the population mean. Since we are saying mean so many times, so I don't want to be mean, and I want to give you another example so that it's clear exactly what we are doing. So take this example of coin toss. And let's say I say tail, I give it a value of 0, variable 0. Head, I give the value of 1. And now in this case, I don't have like an actual population. I just have a probability distribution from which I sample. So it's this kind of a thing, like you have a distribution in your mind from which you sample. But I am given this distribution that 0 or head, or sorry, tail, and 1, which is head. The internet connection is unstable. Okay, so both of them have probability half. In this case, I'm not giving any frequencies. I'm just given a probability distribution from which I sample. And I know when I pick 1, this probability distribution is exactly same as the given one. That's the main assumption of random sampling. So probability of tail is half, and probability of head is also half. Now I pick samples of size 2. So what are the possibilities? I can have head. I can pick first. So in this case, my problem is that I'm coin tossing again and again. So in this case, I'm doing something with replacement. A value which comes up can come again. Well, actually, even in that case, it would come again. It's just that it's an infinite number of things. So this question does not even come up. But these are the values, not the members. So the concept of replacement doesn't even enter here. So you have this head, and you can have head. The first could be head, the second could be tail, or your first could be tail, and second could be head, or you could be tail. So 1, 1 and 1, 0 and 0, 1. This is the same sample. It's just that because I'm doing with replacement, so they both occur twice. This has a probability of, each one of them is equally likely. So a sample like this has a probability 1 by 4. A sample like this, now I'm forgetting the order, has a probability half. And a sample like this has a probability 1 by 4. So in other words, the probability that both of them are head is 1 by 4. The probability that both of them are tail is 1 by 4, but one is head and the other is tail is 1 by 2, because it can occur in two ways. Now let's compute what is the, by the way, population mean. In this case, population mean can only be computed using the probabilities, because it's just a distribution which is given to us. So it's 0 has half the chance, or you can imagine that you have created a population by doing the coin toss a million times, but it will be like half of them would be 0 and half of them would be 1. So the population mean is half. And what are the possibilities of the sample mean of size 2? Sample means are 1 plus 1, 2 divided by 2, 1. 0 plus 1 divided by 2, because the sample size is 2, half. And 0 plus 0 divided by 2, 0. So these are the possibilities. And I've already said that probability of this one occurring is 1 by 4. Probability of half occurring is half. And probability of 0 occurring is also 1 by 4. Now what is the expectation of the sample mean? So sample mean is a random variable now. It has 3 possible values: half, 0, 1, and their distribution is given like this. This is 1 by 4. Expectation value is of the mean is you have first value times its probability plus second value times its probability plus third value times its probability, which is equal to half, which is equal to the population mean. And we can do, we are running out of time, do it for a sample of 3 and you will find, so it's no coincidence that population, the expectation value of the sample mean is always equal to the population mean. So it's a first result, we have a very nice result, and we can prove it in 2 lines based on what you have done in previous courses. So we will look at it next time again. And I think we will have to shift the homework, all the homeworks by 1 week, because we haven't done any much yet. So the homeworks will be given these in the 3rd week, not the 2nd, because this is the 2nd week. So any question?
Sir, will you upload the recorded lecture on
Yes, I
Elements?
will.